Okay, welcome back. So we are in the middle of the discussion of the laminar premix flame, and what we have done so far is that looking at the correlation and their curve for the flame speed, laminar flame speed and the flame thickness. So we will look at more into the details. So this is the curve what we have seen, because we got some correlation and then we obtained this thing. So now what we can do, we can some flame speed correlation we can get, some flame speed correlation that we can obtain. So how we do that, we will get SL equals to SL reference, and there is a T unbound reference to the power gamma, and P by P reference beta 1 minus 2.y. So this is your 6.33. Now this is valid for T unbound greater than equals to 350 Kelvin, and where TU reference is 298 Kelvin and P reference is 1 atmospheric pressure. So what will get SL reference, it will be some constant Bm plus B2 phi minus phi m, which is a square, and gamma 2.18 minus 0.8 phi minus 1, or while the beta is defined as 16 plus 0.22 phi minus 1. So that is what you get. Now we can look at some other interesting things which actually occurs in a premix flame. This is a very specific to a premix flame. One important aspect of it is the quenching. So what does quenching mean? Quenching means that it is a certain areas where flame extinguishes, and this flame extinction can happen due to so many other factors, and we will look at those factors, what are those things that actually cause this quenching to take place. Then flammability limit, this is another important aspect. That means it is not that I can have certain mixtures and the mixture will burn automatically. So that would not happen. And then the ignition, because this is another area or it poses quite a bit of challenge how to ignite the premix flame mixture, because they are quite sensitive to the ignition and can lead to explosion because of some uncertainties. So we consider a steady process where premix flame propagation takes place, then a transient process where flame quenching actually takes place. So in a steady case, this is very much unlikely situation that flame quenching can happen. So flame quenching typically happen when there is a transient situation, and it would be you can think about it, say if there is a flame there, it is a spotty location, ignition also the same thing. Now what are the major factors that cause this extinction? One is the thermal effect, that is heat loss. Let us say the flame is coming close to this is wall, and the flame is coming close to this wall, and there is a heat loss through the wall that could suddenly quench the flame there. Then chemical suppression, that is another factor which may cause the flame extinction. Aerodynamic effect, this aerodynamic effect means what we say, that any burner, fuel and this fuel air mixture, they are injected and injected through some pipelines and other means like swirler or something like that. Now, the fluid dynamics behind those things actually can cause this flame to extinguish also. This is what we mean by aerodynamic effect. Now, we will go one by one and look at what happens when quenching takes place by a cold one. Now, the flame front, especially the premix flame front, can get extinguished when it enters through a sufficiently small passage. That means, if you allow to pass through a very small passage, then it can quench. That is one of the ways it may possibly happen. If the obviously the flip side of it is that if the passageway is large enough or broad enough, then the flame will propagate through it. Okay. Now, which immediately brings to an important question, how do you estimate the quenching distance? That means, I have a passage through which the premix flame is passing through and you want to estimate the quenching distance. So, this one can identify as a critical diameter of a tube or critical distance between two flat plates through which a flame will not propagate. So, that essentially you think about a simple geometry like this, these are the two flat plates and the flame is passing through that situation. So, that is a critical distance through which the flame will not pass through, that is your quenching distance. Now, there is another phenomena which quite often happens in premix flame, especially in a lean operating condition. Now, this is called flashback. What means that if this is my at a schematic, this is my combustion chamber and this is my upstream mixtures, fuel plus air which is coming in. Flame is supposed to be here within the combustion chamber. Because of some level of uncertainties or changing operating conditions at the upstream or here, this flame will propagate upstream and may sit in the upstream block. This is my upstream block. Now, whether this is a desired phenomenon or not, absolutely no, because if this happens, then if the flame sits on the upstream pipeline or upstream section of this whole system, this can cause severe damage to the upstream injection system and all these things. Now, which will not only the detrimental from the structural point of view, also it is not safe, because that can lead to any other accident. Now, does the flashback happen all the time? Not. It is a very specific situation when flashback happens, that this you operate the lean premix condition. Usually normal operating condition flashback does not happen. When you try to operate at the lean premix condition, then flashback is likelihood possibility. And why? Now, these are all one after another connecting questions, because flashback happens because of lean premix condition. Now, why would one operate the system at the lean premix condition? Because this will reduce the NOx or emission. So, the lean premix condition has advantage on the emission. So, this will have a low emission. So, that is why this is a requirement from the health or environmental point of view. That is why try to operate at the lean, but if you operate at the lean, there is a likelihood possibility of flashback. So, that means again the whole point which comes here, As we slowly getting deep and deep of the discussions, you can see how things are connected, which we started up in the introduction showing some pictures that what could happen or what could not, but here you see, because that is why the whole issue is that it is an optimization problem with multifaceted issues, it is not a single dimensional problem. You need to operate under at lean condition, but then lean condition also not only flashback, where it will be also lead to a blowout. Now, these are the some of the things which we are talking that flashback can happen if the reactant flow rate sustaining a laminar premix flame is significantly reduced or shut off, and the passageways upstream of the flame are larger than the quenching distance. So, these are some of the thumb rules where people think that then the flashback can occur. Now, how do you determine this quenching distance? So, one can do experimentally that the tube burners for the quenching diameter, that is one thing. Then high aspect ratio slot burners, that could be another thing between two parallel plates. Now, there are some criteria that one can put together. One is that ignition will occur only if enough energy is added to the gas to heat a slab about as thick as a steady propagating laminar flame to the adiabatic flame temperature. So, that is what one criteria that ignition will take place. Now, the second criteria says that the rate of liberation of heat by the chemical reaction inside the slab must approximately balance the rate of heat loss from the slab by thermal conduction. If this is a slab, so what about of heat generates here, the heat rejection through there also should balance out. So, now you can use these criteria and can develop a simplified model for quenching. So, to do that simplified analysis, what one can do, take an simple box like this is the control volume and the distance is d between these two plane. Here is the loss due to conduction and this is the generation. So, the energy balance, if we write, so energy balance if we do, so it is equating the heat produced by the chemical reaction to the heat lost through the conduction. So, that means Q dot V, Q dot conduction of the total conduction losses. So, that is your 6.34. Now, this volumetric heat release is related to the reaction rate. So, this is nothing but my average reaction rate into delta Hc. So, they are connected like that. And what is that? The average reaction rate, this is in terms of T burn minus T unburn with the limit of Tu to Tb m dot f dt. This is what we have earlier. Now, through the slab of the wall, the heat loss by conduction which follows the Fourier's law. So, we can get the conduction heat loss is nothing but kappa A dt by dx at T wall, where both temperature gradient, this one dt by dx and kappa are evaluated at the wall temperature, that at Tw. Okay. Now, area is 2 delta L where L is the slot width. Now, the temperature gradient is not straightforward to evaluate, that we have already seen earlier, that dt by dx. So, one can have a lower bound for dt by dx. Now, this evaluation of dt by dx is little tricky. So, the lower bound of that Tb minus Tw by d by 2, that is the lower bound. So, what does it assume? This means there is a assumption behind that, and which is a linear distribution of T profile. So, this linear distribution will give you this lower bound. Now, what may possibly happen, that your dt by dx could be higher than this, or is likely to be greater than this one. So, we introduce a constant b. So, we are introducing constant b, which is defined as dt by dx, the magnitude of that db minus Tw by d by b. So, some parameter that we introduce, so that the boundedness can be maintained, where b must be greater than 2. So, that means it will satisfy the lower bound and the upper bound also. Now, what we can do, this is our equation number 37. Now, we combine equation 35 to 37. So, we are combining all this. What we get, that minus delta AC delta dl equals to kappa to delta L Tb minus Tw d by b. So, this is our A, or one can write d square equals to 2 kappa b Tb minus Tw minus delta Hc. So, this is our 6.38 b. Now, one can simplify this equation. How one can simplify? By, if we assume T at the wall is the T unburned, and also we can use the relationship of SL equals to 2 alpha nu plus 1 F by rho u to the power half, where delta Hc is nu plus 1 Cp Tb minus Tu. Then we can simplify this guy 6.38, and that simplification gives me that simplification of 6.38 b, which gives me d equals to 2 b alpha by SL, or d equals to root b delta. So, this is an correlation that one can get for the quenching distance with the premix thickness. Now, if we plot that thing, this this is my flame thickness, that means this side is delta, this is quenching distance, that is d millimeter, and this side is my phi. Now, there is a nice variation of the flame thickness. Now, the solid curves, this is for delta. So, one can see that as you increase the equivalence ratio, delta comes down, that means the flame thickness reduces, then slowly it again goes up with the increasing equivalence ratio. There is a similar pattern which is followed by quenching distance d. It also starts somewhere at the lower equivalence ratio and it comes down to somewhere close to the stoichiometric one minimum, and then again goes up. So, that is quite obvious because d is directly proportional to delta, but with a factor b. So, the pattern of delta would be reflected in d as expected. Now, we talk about the flammability limit. Now, the premixed laminar flame will propagate only within a range of mixture strength. One is the lower limit, that is lean limit of flammability, that means phi less than 1, or it will be the other side of it, that is the upper limit or the reach limit, which is phi greater than 1, because phi equals to 1 is stoichiometric condition. Now, this is quite frequently quoted as percentage of fuel by volume in the mixture or as percentage of the stoichiometric fuel requirement, because then see people might talk, if you go and look at these gasoline fuels in the gas station or the petrol pump or the diesel pump, you will see there is a limit they mention. So, these are the things that any particular fuel, it has an flammability limit. Beyond this bound, there would be unlikely to reaction to happen. Now, it is also known that whether or not a flame initiated at the bottom of the vertical tube propagates the length of the tube. And flammability limit, this can be measured under conditions which are not influenced by quenching effect, that is the reaction tube must be of suitably larger diameter, that means there is no quenching taking place. Then that means you are allowing to have complete flame structure, and then only you can measure this limit, that what is the lower bound and what is the upper bound where actually the flame extinction takes place. Now, the ignition source must be of sufficiently energy to guarantee the ignition, otherwise the property under investigation would not be limiting the ignition energy. Now, there are some common terms, or you can get, there are huge variant of fuels which exist today and their flammability limits are also quite variable, because that is expected. For example, acetylene it is 2.5 to 80% by volume. For propane the range is 2 to 9.5%. Now, there is some correlation which has been observed with the flame temperature or the minimum flame temperature. Now, the important thing is that this existence of flammability limit is predicted by theories of flame propagation, provided the heat loss from the burnt gas is included. Okay. Now, similarly, one can look at this, this is propane, and there is a representative curve for propane when it is with the percentage of oxygen, the reaction goes on, what happened to that mixture. So, you can see this side of the curve is this is your nitrogen formation curve, which goes like this with the percentage of oxygen, and this is your stoichiometric mixture, means phi 1 condition. this is your CO2 formation, how that behaves. So, that means this plane, along this plane there is a variation of phi, one can think about, that is why the species will go like that. So, this side is the extinction limit, that means beyond this level or above this percentage of the propane there will be no flame, or this side there is a flame propagation. So, that will determine. So, every fuel one can determine this kind of limits and the boundedness, which will allow you to have an idea, the idea of these flammability limits. Now, we will move to the third point, which is ignition. So, what here we wanted to look at is that, or the objective is that to on minimum ignition energy. That means, what is the minimum energy that is required to move the reaction forward. So, that is what is quite important. Now, we will limit our discussion to the ignition of a premix gas by spark only, and if you go to the textbook, you will find there are other methods also or other ways to do that analysis. So, you are always welcome to go through that, but we will restrict so that it will give you an idea how to get the ignition done. So, the spark ignition engine, where it is used, it is in gas turbine engine, it is in gasoline engine, which is the spark ignition engine. That means these are your petrol engines essentially, which are two wheelers or four wheelers like cars and all these things, industrial, commercial and residential burners. Now, important thing for this is the ignition energy and its dependence on the temperature and pressure, because there is a direct dependency. Now, how we will go about the simplified ignition analysis? We use the second criteria of the ignition and quenching. So, that is our first thing. Then we define a critical gas volume radius such that the flame will not propagate if the actual radius is smaller than the. So, that means we will define something like that, that there is a critical radius, beyond that there will be no flame propagation. So, assume the minimum ignition energy to be simplified by the spark is the energy required to hit the critical gas volume from its initial state to the flame temperature. So, that means if you define a gas volume, idea is that what is the minimum energy the spark would be used to get the flame temperature from its initial state to get the flame temperature. So, this is how we will going to do the analysis, and we will stop here and continue the analysis in the next lecture. Thank you.